Hello. Today we're going to keep going in chapter 11. We're going to look at the comparison tests. So there's two of them, and we're going to see them both. So the idea here with these comparison tests is where we have a given series and we don't know if it converges or diverges. And we have to compare it to another series that we know something about. And right now we're going to look at series that only have positive terms, because then we compare corresponding terms to see which are larger. And that's called the direct comparison test. It's just a term-by-term comparison. Or we look at the ratios of corresponding terms, and if that is a constant, if it's just a number, then one series term by term is that number times as big, and so that doesn't affect convergence and divergence. So these are very different tests, but they both have the word comparison in them. So to show you how this works, we're going to start with the direct comparison test. This is just a quick example how this all works. There's two series, and the idea is we'd want to know about this one, but we can't do this integral, right? We can't use the integral test here; it'd be too crazy. And we know about this series. So the idea is, if we can compare this series to this one on a term-by-term basis, it'll tell us something about the convergence. So this one over here is geometric, right? It converges. And what we want to look at is term by term. So for every n in this sum, this term is smaller than this one because the denominator is bigger, right? So bigger denominators means all other things held equal, bigger denominators means smaller terms. So if every term, so if you graph it, the term by term, the dot for this one would be sitting underneath the dot for this one, right? And that means that the sum has smaller terms. So once we compute the sum of this sum has to be smaller. Well, we already computed this sum in a previous section. And the partial sums here are bounded by 1, which is the sum of this overall. So if this whole sum is 1, then none of the partial sums can ever be bigger than 1. Even if we don't know what the partial sums are, they are bounded. They are increasing because every n we're adding a non-zero positive amount, and therefore they converge. So that's why these things have to be positive series, because we need to use the theorem that says that a bounded monotonic sequence converges. So we used that in previous sections, and we're using it again here. So that's the idea. Both of our comparison tests we're going to see today work similarly. So here's the rule for the direct comparison test. That's the one I just showed you. We have two different series with positive terms only. The Bn is what we call the comparison series. This is like the original series we're trying to learn about, and this is the comparison series. So if the comparison series is convergent, and every term in the original series is smaller than its corresponding term in the comparison series, then the original series is convergent. And that's what we just saw in the previous slide, right? Well, it turns out that the sort of the inverse of this is true too, right? The contrapositive. If our comparison sum diverges and each term is larger, then terms that are larger than something that diverges. So this is not the same as the integral test, right? The integral test, it doesn't matter if the series is larger or smaller. But when we're doing direct comparison, it does matter. Because with our integral test, every point we were comparing was on the function that we were integrating. Here, these series that we're comparing are not directly related. We're sort of building some sort of relationship and investigating it. It's not a natural relationship. So it's not the same rule as the integral test. So as we progress through chapter 11, we start picking up more and more tests. You got to really keep track of specifically and precisely what the rules are for each test. There's a bunch of them. Oh, and here's one more thing to keep in mind as we work through. Don't mix up sequences and series. A sequence is a list of numbers. A series is a sum. So when we have a series, the sum of the AN, each series comes with two associated sequences. One is the terms themselves, and one is the partial sums. This is very commonly messed up by Calc 2 students. Just remember, the individual terms matter for the divergence test, but the partial sums matter for just about everything else that we're going to see. All right, now we're going to look at the two main types of series that we use to compare. If your original series or your original terms contain polynomials, rational functions, or algebraic functions, you want to do a comparison with a p-series, right? And the p-series converges if p is greater than 1, and it diverges if p is less than or equal to 1. If your terms in your original series contain exponential functions, then you wanted to compare it to a geometric series. This is not a rule, this is just a guideline. We're going to see the last example we see in this section today. We have to figure out what to compare it to. So it's not always very simple. But if you are given polynomials, rational functions, algebraic functions, definitely do p-series. And if you're given exponential functions, definitely do geometric series. And here's why we do it. When you have polynomials, rational functions, and algebraic functions, you always have n to some power. Whenever you have exponential functions, you always have a number to the n power. So we're broadly classifying things by where, like what's in the exponent, right? If it's just a number in the exponent, p-series. If n is in the exponent, geometric series. That's the main rule. Again, there are further refinements of these standard series. We'll see some of them, and as we progress through in chapter 11, we'll definitely see more. All right, let's jump in. We're going to use direct comparison test here to determine whether the series is convergent or divergent. So this is very investigative, this process. Many calculus students have sort of made their way to this point so far by just looking up a similar problem. It doesn't work, because we can ask these questions millions of different ways. So use what you already know. So here's what we're going to do. It looks like a p-series because it's polynomials. Well, it's actually a rational function, right? It's a polynomial divided by a polynomial. So that makes it look like a p-series. So what we have to do is manipulate the terms, and that'll kind of tell us what comparison to make. So let's go back and look at our p-series again. Notice the p-series is 1 over n to the p. So we want to try to get a 1 or just a number in the numerator. We want to get all the n's out of the numerator. So we're going to divide by the highest power of n in the numerator. This is different than limits, what we did before. We're not taking a limit here. We're just comparing. So here we have an n. We'd like this to be just a number. So we divide everything through by n. Then we simplify. So n over n is 1. 5n cubed over n is 5n squared. And then 2 over n stays 2 over n. This tells us what to compare. Now we just look at the highest power in the denominator and make a direct p-series comparison. Keep all of the numbers the same. If there's any coefficients, keep them in there. So 2 over n is a positive number. It's bigger than 0. It's never 0. And as n increases, this thing gets smaller and smaller. But it's still a positive number. So this whole thing here is smaller than this whole thing because this denominator is bigger. This over here is a p-series. So even though we have this little extra bit here, it doesn't matter. We don't care about it. We only care about this. we can pull the 1/5 out, and now we have a p-series. We know about this p-series. We've studied it a bunch, right? This thing definitely converges. Any p-series where p is greater than 1 converges. So because this converges, and this whole thing is less than that, then our original series also converges. So the direct comparison test is really easy to use. The only time it messes up is when people choose the wrong comparison. If that happens, you'll know right away. And that's okay. It's okay to choose incorrectly. But again, it's a very investigative sort of process. You're not just going to get this stuff by doing a bunch of examples and hoping you've covered everything. You've got to follow the rules, make sure you know the rules, make sure you're thinking through the rules, and then execute the rules one at a time very slowly until you get the hang of it. So you're going to want to go back and do all of these examples again before you try the homework. I'm not doing a ton of examples. I'm trying to keep these videos under 35 minutes. But you can do the examples in the book. There's videos to watch, lots and lots of stuff like that. Moving on. Let's do another one. We're going to do another direct comparison test. And just looking at it, you can see now we have n's in the exponent. So that tells us we're probably going to want to do a geometric series. Right? It looks like a geometric series. So we manipulate the terms again. So this is what we're given. Notice that the geometric series, I need to have n minus 1 or n. Here I have an n plus 1. I really don't like that n plus 1. So I pulled the n to the front. Didn't really like it there. I want these to be the same power no matter what. When these are the same power, I can show that this is greater than this. Again, denominator smaller, so terms bigger. This doesn't quite look like a geometric series yet, but now it does. Keep in mind, it doesn't matter what this power is. I know the geometric series is supposed to be n minus 1. You can always just pull a term out and put it in the front. Either way, the convergence or divergence of a geometric series does not depend on the initial term a. It only depends on r. So we can see that r here is 9/8, which is bigger than 1, so it diverges. So don't worry about trying to get it to look perfect. You just want to get it to the point that you know what r is, and then you know if it diverges or converges. So if our comparison series diverges, and our original series was bigger than a divergent series, that means that the original series must diverge as well. So most students do fine with the direct comparison test. The only problems that you run into in this chapter, and you'll see as we go, is just when you have lots and lots of tests, which we will. I think we end up with 8 of them. You got to know which test to use. And it takes some trial and error. It's like in chapter 7, techniques of integration. It's a lot like that. You just got to try different stuff and see what happens. All right, now we're going to learn about the limit comparison test. That's the second test we're going to see today. Well, it turns out that the direct comparison test that we just used is conclusive only if the terms of the series being tested are smaller than those of a convergent series or larger than those of a divergent. So we saw one of each. We saw a p-series. We saw a geometric series. If the terms are larger than the terms of a convergent series or smaller than those of a divergent series, then the direct comparison test doesn't apply. In many of these cases, we can use the limit comparison test. So you might be thinking, well, why do we even need a direct comparison test if we have this limit comparison test that always works? Well, the limit comparison test has some problems, and generally speaking, it is tougher to use because it involves limits, which means L'Hopital's rule can kick in and all kinds of stuff like that. The direct comparison test, all you need to do is manipulate the expression until you have an answer, and then you're just done. Here, we manipulate, and then we have to take a limit, and other stuff can happen. So here's the limit comparison test. Again, our original series and comparison series must have positive terms. If the limit of the ratios of the individual terms, this is not the partial sums, these are the individual terms. If the limit of the ratios of the terms is a number, c, where c is finite but greater than 0, it obviously can't be negative because every term in these series is negative. Is positive. So you can't divide a positive by a positive and get a negative. So if we get a number here, then either both series converge or both diverge. This is pretty interesting. It's pretty powerful, but again, it is flawed. It is based on your choice of a comparison series. If you choose badly, you might get c equals 0, which is inconclusive, and you might get c equals infinity, which is inconclusive. That's the last slide. I'll show you how that works. The c equals 0 and c equals infinity. I'll show you how it works later. So again, we're going to take the an terms divided by the bn terms, take the limit as n goes to infinity. If we get a number that isn't 0, then whatever happens to the comparison series happens to the original series. And again, we're going to choose a comparison series that we know what it does. That's the idea. All right, so let's determine convergence or divergence here. So just looking at it, we really don't know. But you might look in the denominator and see that we have a square root of n squared. So the square root of n squared is, and we're only dealing with positive terms, so the square root of n squared is 1 over n. So that tells us that that's a good comparison series. It looks like a p-series. These are algebraic functions. So you really just look at the highest power in the denominator to come up with a p-series. Now, if we had an extra n in the numerator, we'd have to divide through by the highest power in the numerator first, then look at the comparison p-series. But there's nothing in the numerator, so we don't have to do it. So 1 over n is going to be our comparison series. So we just fill everything in. So here we're dividing by a fraction, so I'm going to flip and multiply. Then I'm going to distribute, and I'm going to try to divide out the highest power in the numerator. So n, once I multiplied this through and got 8n, now n is the highest power in the numerator, so I got to get rid of it. So I'm going to multiply by 1 over n. That'll get rid of this n. Remember, 1 over n is the same as 1 over square root of n squared, right? We got it right here. Because this has a radical, I need this to have a radical, or I can't multiply in. So when I multiply, I'm going to get 8n over n. I'm going to get 8. And down here, I'm going to get n squared divided by n squared, and 9 divided by n squared. This is just 8. This is just 1. And this is 0 when we plug in as n goes to infinity. So 8, 1, 0. 8 over the square root of 1 is just 8. And so because our comparison series diverged, 1 over n diverges, right? That's a p-series, p equals 1. That's actually the harmonic series, right, that we studied in detail earlier. Because this is a number that is not 0, whatever this series does, our original series does too. So they both diverge. And that's pretty much how it works. Again, lots of algebra here, lots of limits. One thing I want to warn you about is because you're doing a limit comparison test here, L'Hopital's rule does not work with equal powers. It will break. So please do not try to use L'Hopital's rule. There are things later on that we're going to use L'Hopital's rule that works, but this is not one of those cases. Please use the algebra version of reducing these things instead of L'Hopital's rule. At least till later on when we learn some more stuff. All right, last one, limit comparison test. So this is 1 over n factorial. Factorial is where you take every number and multiply it by the whole number that's less than that number. And it doesn't look like a p-series, and it doesn't look like a geometric series. So what I decided to do is look at the first few partial sums, and it looks like it converges really fast. So I only did 20 terms, and it converged really fast. So I'm thinking this thing's going to converge. Now we have to decide, do we compare it to a p-series, or do we compare it to a geometric series? And you really just got to try stuff and see what happens. So I tried a geometric series because I noticed that multiplying these numbers together was always less than just multiplying a bunch of 2's together, right? As soon as I get past 4, they're equal. And again, I'm taking big numbers here, right? I'm looking sort of at the limit as n goes to infinity, right? So I'm not really worried about, I mean, sure, 2 is bigger than 1, but as I multiply these bigger and bigger numbers together, clearly, as n increases, this is true. So, if the left side is always bigger than the right side, that means if I put it in the denominator, the left side is always smaller than the right side. Bigger denominator means smaller terms. So that means that this sum is always less than this sum. Right? Because the denominators are bigger on the left side. So this, when we put them in the denominator, the overall sum is smaller. Well, this is just a geometric series. It doesn't look like one here, but it is. And again, we don't care about a. We don't care about the initial term. We only care about r. Right? This r is less than 1. So this comparison series converges. And because the ratio, well, this is just a comparison. We actually didn't do a ratio here. Can't do one because you can't really divide. Can't really divide this stuff, right? So this is, it's considered a comparison, not a limit comparison. But the idea is that just sometimes it's not as simple as we're comparing it term by term or we're making a ratio. You've got to sometimes get in there and fiddle with it. So back to this slide. This thing converges, and so the overall original series converges as well. So this is actually just the ordinary comparison test, the term-by-term comparison test, not the limit comparison test. All right, one more thing to talk about, and then we're all done. So this is the limit comparison test again. This is the last thing. When c equals 0, it's conceivable that you could just make a bad choice and get c equals 0. It turns out that it doesn't tell you anything about what's happening. You could get numerator converge, denominator diverge. Both converge, both diverge. It doesn't tell you much. If you get c equals infinity, you could get numerator diverge, denominator converge. Or you could get both converge, both diverge again. If that happens, if you get a c equals 0 or c equals infinity, then you have chosen your comparison series incorrectly, and the results of the limit comparison test are considered inconclusive. So this is one reason why, unless you're sure what's going on, the limit comparison test is generally one of the last choices. Because if you choose wrong, the test can just be inconclusive, and then you haven't really learned anything. So as we progress through Chapter 11 and pick up more and more tests, you know, if you can do the integral test, sometimes that's better. If you can do the comparison test versus the limit comparison test. And we're going to pick up even more tests in the next couple videos. So don't worry, no shortage of tests. All right, well, that's it for this video. If you got any questions, let me know. And I'll see you next time when we look at alternating series. Bye-bye now.